And welcome back. Let us do it. Let us do this thing. Okay, so gaseous reactions. Now, okay, if you have, all of your stuff gathered together, all of your reactants, at the same temperature and pressure, okay, the volume of each of your each of your things is going to be proportional to the total number of moles. So if you want, you can work in volumes instead of working in moles. Again, volume is easier to measure than moles. You can measure volume directly, that is to say. Or you can go the other way around. At a given temperature and volume, pressure will be proportional to moles. And pressure is often even easier to work with. It's harder to keep pressure constant and vary the volume in some cases. Sometimes it's easier to keep volume constant and let the pressure vary. So constant pressure varying volume means you're working with a piston. You're working inside of an engine. Constant volume varying pressure means you're working with a sealed container, a flask or a beaker or something that has been stoppered up. So you can work with either one. And in either case, you have something that is easier to work with than trying to measure moles directly. Because you can't measure moles directly, but you can measure pressure or volume directly. That's easy to do, depending on your setup. Okay, so if you have, for example, water, the reaction to make water, you have hydrogen plus oxygen making water. 2 liters of hydrogen gas plus 1 liter of oxygen gas will make 2 liters of water. Gaseous water, that is, not 2 liters of liquid water. Similarly, you could mix, in a single container, 2 atmospheres of hydrogen plus 1 atmosphere of oxygen, and the result, after they go boom, would be gaseous water at 2 atmospheres. So either way, you can track the progress of your reaction by measuring pressure or volume changes. Okay, in either case, for water, you'd be changing either from 3 atmospheres down to 2, or 3 liters down to 2. And you can also mix and match the different substances involved, such as, for example, calcium carbonate, limestone. When you heat it up, it will produce a solid calcium oxide and the gaseous carbon dioxide. So you can play around with these things. And let us do exactly that, starting with this final example here, calcium carbonate plus decomposing to form calcium oxide and carbon dioxide. So, if we have 5 grams of calcium carbonate in a 100 milliliter flask that has been evacuated, it's a vacuum, 0 pressure, let's simplify things a little bit. What is the final pressure going to be inside of our flask after we decompose all this calcium carbonate? Well, obviously, first things first, we're going to need to convert from grams to moles. So, the molar mass of calcium carbonate is 100.09 grams per mole. So, 5 grams calcium carbonate divided by 100.09 grams per mole is equal to 0.04996 moles of calcium carbonate. Then, we use stoichiometry to find out how much carbon dioxide this is going to produce. This is a wonderfully simple little equation, 1 to 1 to 1 to 1 to 1. So, it's going to be 0.04996 moles of calcium carbonate times 1 mole of carbon dioxide per 1 mole of calcium carbonate is equal to 0.04996 moles of carbon dioxide. And we only need to worry about the moles of carbon dioxide because calcium oxide is a solid. It's not going to contribute to the pressure inside the flask. And let's go ahead and simplify things a little bit further by just saying that the volume of calcium oxide is equal to 0. Not only does this make things easy, but it keeps me from having to look up the density of calcium oxide. Okay, so the pressure exerted by carbon dioxide is going to be equal to nRT over V, moles times R times temperature. I keep on forgetting to include temperature, don't I? Okay, let's say it's 80 degrees Celsius, okay, divided by volume. Okay, so when we plug those numbers in, that gives us 0.04996 moles of carbon dioxide times 0.08206 liter atmosphere per mole Kelvin times 353.15 Kelvin conversion divided by 0.1000 liters conversion. And once we plug that into our calculator, it gives us 14.48 atmospheres. That is a lot of pressure. In other words, that cork is going to come flying right on out of there. Okay, that was a fairly simple, fairly straightforward problem. And the next problem is going to be a little bit less simple, a little bit less straightforward. I think you're going to hate me, or you would if I were to give it to you for homework or on a test. Fortunately for you, I'm the one who had to suffer through this. So let's go ahead and take a look at this, our next example. Okay, so let's say that you have iron and oxygen in a flask. Okay, that is to say, you just take a piece of steel wool and you drop it inside of a flask. You use acetic acid, HC2H3O2, that's vinegar, as a catalyst because when you do that, iron rusts. I mean, it's not super duper fast, but you can actually observe it. It's about as interesting as watching paint dry, but you can observe it. Okay, so iron plus oxygen in the presence of an acetic acid catalyst produces iron oxide, rust. Fine, great, wonderful. So, in this case, it is 1 milliliter of iron and 1 milliliter of vinegar catalyst inside of a 100 milliliter flask at room temperature and 1 atmosphere. What is the final pressure inside the flask once this reaction has proceeded as far as it can go? This is going to take a little while. When I say as far as it can go, that means that we're looking at a limiting reagent problem. We need to find the moles of iron and oxygen we have available to us before we can find out how far the reaction will go. I mean, which one is going to run out first? It's a small flask, so there's not much oxygen in there, and that's a small amount of iron. 1 mil, 1 cubic centimeter, that's like about the tip of your pinky. So it's all told not a whole lot of either one. How are we going to do this? Well, I certainly didn't make it all that easy. Okay. First, you need to look up the density of iron at 20 degrees Celsius. That's 7.85 times 10 to the 3rd kilograms per cubic meter. Ugh. So we're going to need to do some conversions. Fortunately, we already know that 1 milliliter is 1 cubic centimeter. Boom, straightforward. So 1 cubic centimeter. Let's go ahead and convert that to cubic meters. 1 cubic meter is 100 times 100 times 100 cubic centimeters. There's 100 centimeters in a meter, so there's 100 to the 3rd cubic centimeters in a cubic meter. Then we multiply by our density, 7.85 times 10 to the 3rd kilograms per cubic meter. And let's go ahead and convert those kilograms to grams, so 1,000 grams per kilogram. And finally, we'll convert from grams to moles. There are 55.85 grams in 1 mole of iron. Now let's go ahead and double check. Yep, centimeters cancels out. Cubic centimeters and cubic meters cancels out. Kilograms cancels out. And grams cancels out, leaving us with moles. And once you plug all those numbers into your calculator, you end up with 0.141 moles of iron. That's an awful lot of work, but we got there in the end. And what about oxygen? Let's go ahead and write down the number of moles of iron up top so we don't forget it. But oxygen makes up 20.95% of our atmosphere. That's 20.95% by volume. Now, volume is nicely proportional to moles, which means that the mole fraction of oxygen in our atmosphere is 0.2095. Yay! It's something simple. Okay, so the partial pressure of oxygen is going to be the mole fraction of oxygen times the total pressure of our atmosphere. So it's 0.2095 times 1, let's go ahead and just call it 1.000 atmospheres. I am the guy making up the problem. I can arbitrarily change the Sig Figs if I want. And the partial pressure of oxygen is 0.2095 atmospheres. So we're partway there. Let's keep going. So now let's go ahead and plug this useful bit of information into PVNert. PV equals nRT. So we rearrange and N equals PV over RT. Let's start plugging in some values. Okay, that's 0.2095 atmospheres times 0.0980. What the hell? Where'd that come from? Well, we started out with 100 mils, and we had to subtract the volume of iron and the volume of acetic acid in there. I'm tricky like that. Okay, now divide by 0.08206 liter atmospheres per mole Kelvin and 293.15 Kelvin. And that gives us, once we plug it in our calculator, 8.53 times 10 to the negative fourth moles. Yep, that's a really small number. That's 0.000853. Okay, very tiny. Okay, so this is where we're at. We have these two numbers, 0.141 moles of iron and 8.53 times 10 to the negative fourth moles of oxygen. You might think it's obvious which one is going to be the limiting reagent, but let's go ahead and be punctilious about this. Okay, let's go ahead and divide each one by the coefficient. Okay, let's do the stoichiometry thing. So divide by 4, we divide by 3. That gives us 0.0353 for iron and 0.000284 for oxygen. So oxygen is, in fact, the limiting reagent. You're so smart, you figured it out. Good for you. You knew about that beforehand. And thank Christ, oxygen is the limiting reagent. If iron had been the limiting reagent, this would be a much more difficult problem. But because oxygen is the limiting reagent, that means that all of the oxygen is going to get used up. So that means that the total pressure inside the flask is just going to be the pressure of everything other than oxygen. So the total pressure inside the flask at the start was everything and oxygen. So the final pressure is just going to be that initial pressure minus the pressure of oxygen. So it's just going to be 1.000 atmospheres minus 0.2095 atmospheres from oxygen, leaving us with 0.7905. Oh, I caught you, didn't I? Yeah, you almost forgot about the Sig Figs. Okay, yeah, you need to, cut it off at the last significant digit of the one with the fewest, whatever. Okay, so here we draw our dotted line, and so that's where the cutoff is, and we round it out, and the actual answer to this problem is 0.791 atmospheres. That was a nasty as hell problem. I absolutely will not give you something like that on a test. Not even if I was feeling particularly mean or ill-disposed to one of you, Richard. But I would give you something much simpler than this. I would have to, otherwise I would make, let's say, Hannah. Hannah would cry, and I don't want to make Hannah cry much. So that is another example of, another example of a gas reaction, okay, the sort of work you can be expected to do. And that does it for this lecture, which does it for the unit, which does it for Chemistry 1. And unless I am gravely mistaken, this is the last video of mine you'll be watching, unless you take my class again next semester. I kind of hope you do. I like you guys, except Richard. Okay, I'll see you around, and I hope the test doesn't make you, Hannah, anyway, cry. So long.